Good morning. It's my great pleasure to be session chair for the first invited talk here, and the speaker is going to be a very good friend of mine, and this is a real honor for me, therefore, Dieter Fox. Dieter Fox has studied computer science at the University of Bonn, got his PhD in 1998 over there, moved to Carnegie Mellon University as a postdoc, and got an offer from the University of Washington in Seattle a few years later, where he's heading still then the Robotics and State Estimation Lab. Dieter has also been head of the Intel Research Lab and will shortly be heading a group at NVIDIA and setting up a research lab over there as well. Dieter has numerous accomplishments in robotics, state estimation, navigation and control, SLAM, and many other aspects. He has written more than 200 papers. His work has been cited more than 50,000 times. H-index is 95. So in short words, he's a real superstar of our community. He's not only a superstar, he's also a great cyclist. He's a great person and a great friend of mine. Dieter, the stage is yours.
Thank you. Good morning, everybody. Let's just see if this works. Yeah, thanks a lot for coming to the first session. That's always a tricky question if people show up, but since this is the first one, I guess you're still not that tired. And also thanks for the organizers for inviting me and giving me an opportunity to talk to such a great crowd here. This is actually one of the rare cases, I guess, where the presenter has a much nicer view than all the audience. So if you turn around, you see that I'm actually looking out there and I can see some float planes landing and taking off. So if at some point I start dreaming and looking out there, then you know that something's going on there. I'm sure all of you have heard something about deep learning. And it's one of those cases where a learning technology had huge impact already on areas like computer vision, natural language processing, and also speech recognition. And it's starting to get more and more traction also in the robotics domain, especially because of its ability to learn representations from raw data. But interestingly, whenever you start a discussion with people about deep learning, things quickly get very heated, where you have people on the one hand side, they love deep learning, they say deep learning is going to solve all the problems we might ever face in robotics. You just throw a big network at your data and just let it train, and in the end you have your solution, your robot can do everything. And then on the other hand, you have, let's say, the more, what I might call the model-based crowd, where they say, no, I don't need any learning because I just design my model, I can explain everything through my model, and they work just extremely well. And this whole deep learning stuff is never going to generalize anyway. I actually, from my background, especially on the perception side, come very much actually from a model-based perspective. And but over the last years, we've seen also some progress, especially in applying deep learning in this context, especially on the perception side. And I want to share with you today some kind of thoughts on how this model-based and the deep learning-based approaches, how they can hopefully contribute to make robots much more capable in the future. And I hope at some point we can, instead of just fighting each other about models or deep learning, we can all be friends again. Okay, so what I'm going to do is I'm first going to give you some examples from the work we've done on, let's say, model-based perception, which is a lot of kind of mapping and things like that, and tracking. And also there I'll highlight kind of some of the advantages that you have if you use these kind of models. And then I'll briefly talk about kind of just deep learning, give an example for where we applied in our own context. And then I'll give one more detailed example on kind of learning to predict rigid object motion, which is a case where I feel like we demonstrate the benefits of bringing together kind of deep learning techniques and a model-based view in this. And then, of course, I'm going to have hopefully some time for discussion. Okay. So here's just a very high-level view of what I mean by model-based. It's kind of just some way that allows us as designers to inject and also leverage kind of knowledge, or often even just intuition, of how the physical world works. So it's a very broad kind of idea of that. And for example, it might describe how sensors operate, the geometry of sensors, the geometry of an environment, but also how rigid bodies move through the environment based on dynamics, physics-based equations. And these models can be used, of course, very well if you have estimation problems. And typically what you do is you have your model-based system, and you're trying to match that against the data that you observe. And in control, what you're doing is you use these models to try to find the actions so that you can achieve a desired state or a goal state. So on this slide, you see one of the earliest work we've done in this domain, good old robot localization. This is work back from the last century, literally, if you check it out. So some of you, I think most of you were actually here at that time. But so at that time, the idea was we want to localize a robot in an environment. And what you see on the right side here is a sensor model for a sonar sensor and a robot motion model, which means we explicitly kind of try to describe how a sensor might react when an ultrasound sensor, for example, fires towards a wall in the environment. And then the idea is that you have an expected distance for how far the wall is away, and your sonar measurement is just a noisy version of that distance, okay? And for the motion model we described a model that says that how the robot moves from one point in time to the next point in time, which is mostly just a rotation, a translation followed by another rotation. And these models, the nice thing is you can then put into, let's say, a probabilistic framework. And if you then use a technique like a particle filter, they give you pretty nice, robust estimate for the state of the system. And down there you see the equation, which is just a recursive base filter equation for that. For tasks that are, let's say, reasonably simple, like this, it's actually pretty easy also to come up with these models, right? So we actually just sat down and thought, okay, how is this sonar sensor going to work in an environment? And also we can explicitly estimate full distributions over the posterior, in this case again using a particle filter. In more recent work you see a trend actually in the community where for more complex estimation tasks, rather than estimating full posterior distribution over the state, we're actually just optimizing over a loss function that we're defining over this state. So here's an example, the work that my student Peter Henry did, RGBD mapping, where we are using a depth camera and it moves through the environment. In this case, it's a bay in a wet lab. And we can use kind of model-based knowledge about, for example, how light propagates, the geometry of a camera lens, that the camera motion is smooth through space. So it's a 3D or 6D motion, that objects don't move as much, that most of the scene is static. And using that kind of information, we can incorporate that into a loss function that kind of just describes how we can match one data frame to the next data frame, and then we can stitch all of this together to get a 3D map of an environment. And there are many different techniques for doing this now. This is, again, just one example. But also, again, most of these techniques nowadays just phrase this as an optimization problem where you minimize a loss function. And again, the loss function is defined through these physics-based priors that we put into the system. And when you finish this up, then you can get a map that looks like this, which is actually a pretty nice 3D shape map. And the advantage of such a map is, of course, that you can use it for path planning, you can do collision checks, and you can do also kind of reasoning about objects moving in the scene and, for example, doors and drawers opening or closing. This is just what the map looks like if you reproject the color onto it. So you can see that these are getting reasonably good quality, and they can be very useful for various robotics tasks. Now, if you move on to a scene where things are moving, for example, a person, then we're actually violating some of these assumptions that we just made on the previous slide. So in this case, this is Richard Newcomb. He's moving in front of the camera while he's building his KINECTFUSION map. And you can see that this is obviously not a very accurate model of him. And the problem is that the model, again, assumed that nothing is moving in the scene, and the only thing that's moving is actually the camera. So we can, using this model-based paradigm, we can now say, okay, let's extend our model to not only take into account camera motion, but also model the motion of the scene itself. So this is a technique that Richard introduced when he was a postdoc with Steve Seitz and me. It's called DYNAMICFUSION, where the input is a depth video. And now what we're estimating is actually a motion estimation in the 3D space. Okay, so the scene is not a rigid model anymore, but we're estimating a model along with the 3D motion of the different points in the model. Okay, and these little dots that you see there on the left under in the volumetric motion estimation, these are all collections of so-called SE3s that we're going to visit later again. Here's one example that I have to show you. This is my daughter Carla with a little line there. But what I want to highlight here is really the idea is that just with very low-level physics-based kind of constraints on the system and local frame-to-frame optimization, we can actually achieve pretty good models of the environment that we can then use for various tasks. So again, you can see here that actually the model itself is squeezing and changing, also keeping track of the motion that Carla is performing here. All right, had to show you that. Another technique now that's also kind of, again, highlighting this model-based view is called DART, which was work that my student Tanner Schmidt did on tracking articulated objects. Okay, so imagine in our environments, there are many things that are moving according to certain constraints on their behavior relative to each other. So for example, you can represent a person, or in this case, a manipulator, a BAXTER robot, a human hand, drawers, cabinet doors, all by articulated motion, which means that we have individually rigid pieces that move against each other, and how they move against each other is constrained by, let's say, a kind of skeletal model of the scene. And you can use these kind of models now to track how they move through the scene over time. And I'll just give you one example for how this works, where here the idea is, let's assume we have a model of a manipulator, and this is a simulated example, but the manipulator has an object is holding there in its gripper. It's kind of a 3D view on it. And now we have a depth camera that's looking at that scene, so you can see these black dots coming up. These are simulated depth points. And now imagine that there's a slight mismatch between the model pose and the data. All right? And again, in this notion, all we do is we define a loss function that says how much does my model mismatch against the data, and now we can use this in order to optimize it. And in this case, we have the signed distance function representations, which is not crucial in this context here, but the idea is that we can very efficiently compute for the observed points how far away they are from the model, and we can use this discrepancy in an optimizer in order to match our model against the data. Okay? Now imagine the robot also has, for example, touch sensors, and in these two fingers that you see here, it observes that it's touching actually the object, but the optimizer didn't observe that because it was behind the object. We can incorporate that into our loss function and now optimize over that as well, which means we can constrain the motion such that actually those 2 points should be in contact with the object. Okay? Again, this is just some kind of model-based knowledge we put into the system and then optimize over this. You can see here that these two fingers are actually kind of sticking inside each other. We can add another constraint on the system and say that physical objects don't interpenetrate, and we can add that to our optimization process and then get an estimate that is consistent here as well. Okay? So again, the main point I want to highlight here is that it's all kind of these kind of different constraints are kind of relatively easy to incorporate into these systems. Here's one example now where we're using that on a BAXTER robot. This is in collaboration with Robotics. So here the camera is on the placed on the robot, and the camera is tracking both the manipulator arm and the object itself, right? And then we can incorporate these kind of physics-based constraints. And in this case, the robot's task is to move the cup from one location to another while keeping it upright. But because we can do all of this in real time, if you check out the video panel on the right, we can quickly react to any kind of disturbances. Right? It's pretty easy because you track the object in the hand and you can see that it's not upright anymore, and the robot can pretty quickly then adjust its own pose in order to correct for that. Okay? And all of this is reasonably easy to do in this, let's say, model-based framework. All right. Here's one example. This is not work that I was involved in, but a colleague of mine, Emo Todorov, does a lot of work in model-based optimal control, where he is working a lot on kind of reasoning about context between objects, dynamics, and interaction between them. Here's, for example, in a simulated setting, how you can do dexterous in-hand manipulation. And similar to all the previous approaches, all you do in the end is you're just optimizing over a loss function. Okay, you say that the loss is relative to how fast things are moving, how far you are away from your target configuration, and then you can do these kind of tricks here with this hand. Of course, this is in simulation, but some recent work that they've been doing also with local learning actually achieve some kind of a dexterous manipulation also on a real robot system. But one of the main assumptions here is really that the tracking of the state of the system is highly accurate, which on a real robot system we know is not always easy to achieve. So now stepping back and looking at kind of a high-level view on this model-based approaches, I just want to show you here kind of how I feel like understanding at least the pros and cons and the disadvantages maybe sometimes of the model-based optimization techniques is, so let's assume we have a task space, which means, for example, if you want to do hand tracking or track a person, then the task space is the different poses of the hand or the person. If you want to do optimal control, then the task space are the trajectories or the control signals that you want to generate over time. And here in as a red dot is, for example, let's assume this would be the solution, this would be the correct pose of the robot's hand. And here these white dots represent kind of initial estimates or guesses for what that configuration might be or what the path of the robot should be. And what you wish for is, of course, that you now run your optimization and they all nicely converge to that correct position. Okay? Now, the problem is that in real-world data, the optimization problem becomes very complicated, also because it incorporates things like data association problems. So in the real world, typically what you actually have is you just have a local basin of attraction in which your optimizer actually converges. And if you now run these different instances in this setting, then what happens is that if you're in this basin of conversion, you actually get very good accurate results. But if you're outside, sometimes all bets are off and things might just fail. Okay, let me just give you one example from the previous work I showed you with from DART. So let's assume this is the correct pose of a person's hand. Yeah. So the model is this colored different parts of the model, and the black dots are the observed dots. And let's assume these are different initializations for the pose estimate. So all of them have the same observation, which means the minimum is all the same, the one in the middle. But again, we have kind of just a local basin of attraction, which means if you initialize your DART tracker too far away from the data, then it might do pretty bad things. So if you're close to the data, then actually your optimization works, which you will see in the one in the middle up left. I can point to it from here. You see? So if you initialize it well, then your DART tracker actually converges to the correct pose. But for these other poses out there where the initialization is not as good, kind of all bets are off. Okay? And that is again because it is a very complex estimation problem that is non-convex and that includes data association as a sub-problem. Okay? So what I mean by this is, again, these optimizers can be very accurate, but they typically only work in a local basin of attraction. An advantage of these model-based techniques, on the other hand, is that they are kind of globally applicable, which means that because they model, for example, the physics of a system, they have a broad range of applicability to different kinds of models. Okay, so if you view it again in this kind of optimization illustration here, so let's assume these are different problem instances, and they cover a broad range of different settings. So as long as I can initialize my optimizer close to the correct solution, I'm actually going to be in these local basins and I'm going to go to the correct solution. Okay. Here, so for example, in the DART context, these different dots would be, for example, we can track very different things, right? We can track different kinds of robots, we can track people, we can track hands, and it works well as long as the system is initialized well, which means as long as we have a good 3D model of the thing we want to track and we have an initialization of the pose, the system works actually very, very robustly. Okay? So again, to summarize these ideas that these model-based approaches, on the one hand side, have a broad range of applicability. They generalize extremely well, again, because they mostly model the physics. But at the same time, they are just often local because the optimization problems are too hard. Okay? So now I want to give you just a very high-level view on how I see kind of deep learning and give you one example for how we're using it in our own work. So the ideas, and this is inspired by a talk David Silver gave, a tutorial on deep reinforcement learning. Where the idea is simply we have a sequence of functions, and these functions are parameterized via some parameter vectors wi, and we have an input x, and then we just apply these functions one after the other to the input of the previous function, and then we get an output y. And these intermediate representations h, these are kind of the different feature representations that might become more and more complex as we apply more and more functions to them. Okay. Now, the main trick, what makes deep learning work so well, is actually how we can learn these functions. So if we assume that the functions are all differentiable, then if we would like to compute the gradient of this sequence of functions with respect to a certain output, then we can use the chain rule and backpropagate these gradients backwards through this sequence of functions. Okay? In a deep network, you do this kind of going from the output back to the input. And that can be done extremely efficiently, especially if you have these structures that you have in these deep neural networks. And it's very similar to kind of a forward pass. You just go backwards through these parameterized functions. And we can compute gradients with respect to all these weights. And that is, of course, the key trick when you want to do learning. So now, if we want to do learning, what you have is, let's assume we have a training example, x and y star. So y star is the correct output the function should generate. We're going to take that x and feed it through our sequence. Since we have y star, we now can define a loss function that kind of measures the discrepancy between the output of our deep representation and the desired output y star. That depends on, of course, what you want to do, whether you want to do regression or classification. There are different kinds of loss functions. And now, again, we just apply this backpropagation rule, where we're now going to compute the loss of that function, the gradient of that function with respect to our parameters by backpropagating through these sequences. Okay, that's all we have to do, actually. And once we have now the gradient of the loss function with respect to these weights, we just do a step down the slope of the loss function. Okay, and that's all deep learning is doing. Okay, so we have these nice functions that are differentiable, parameters through weights, and then by backpropagation we just update them, and the technique is called stochastic gradient descent. And we keep on doing this by presenting it more and more examples, and over time the system then hopefully learns weights that give you the correct input-output representation. Okay, and this is the view that we typically have if we have supervised learning. For example, in computer vision, of course, something like ImageNet or so is one example where you give the deep network input is an image and the output is what's in this image, for example, a label or so, and then you train this. And in these settings, these systems have been extremely successful. What I want to show you now is an example that's a bit closer to robotics also, where we kind of want to demonstrate that you do not always need manual labeling of your data, but that you can sometimes leverage model-based techniques in order to automatically generate those labels. And the system that we're looking at here is work that Tanner did, is where we try to learn so-called data associations. Okay, so the goal is you have, for example, an image of a scene. So imagine you have a robot and you want to do mapping of an environment. And one big problem in this domain is often what's called the loop closure problem, which means you start out at a location, you observe the scene through your camera, and now you move around, and let's say 20 minutes later, you get back and you want to recognize that you're looking at the same point in your scene. Okay, so what you have to do is you have to match your current camera image against previously seen camera images in order to determine that you're back at that location and that you can determine your relative transformation, which you can then use again in order to globally optimize your map. And traditionally, this kind of matching has been done with hand-designed features. The most famous ones are, of course, the SIF descriptors, but then recently many different ones came up. For example, Hawk features, Orb features, also in OrbSlam, one of the best systems right now. They're using these features. And the idea is, again, you extract features from your two images and match them by comparing their descriptors, more or less, right? And you use some kind of procedure such as RANSAC in order to do this matching process robustly. What we wanted to look at is if we can learn these descriptors in an unsupervised way without manually designing them. And the idea behind this, why we can hopefully make this work, is this notion of chaining basins of attraction. So let's assume we have a system like KINECTFUSION or DYNAMICFUSION or any of these systems that I showed you beforehand that, as I said, have only local basins of attraction. But in many cases in robotics, the advantage is that we have temporal data. We don't only have a single data point, but we have data points through time. And the change from one data point to the next is not very large. Okay, if you have a camera with a very high frame rate, if it moves through the environment, the motion from one frame to the next is very small. And we can use this, as you will see here, in order to generate sequences of motions that go beyond what a normal optimization step could achieve for you. Okay, so which means that the change from one time step to the next is small enough such that we're always, based on our previous estimate, we're always in the basin of attraction of the next time step. And if we do this, we can chain these estimates together. Even if the tracker, like in this case, fails, we can chain them together and get a trajectory like the green one here that is globally, or at least in this local framework, reasonably consistent. Okay, and the idea is now that we can hopefully use these traces through the state space in order to train a deep network to do more global reasoning rather than the only local chain-based reasoning. And here's how this works. So the idea is, imagine you have a KINECTFUSION map. So KINECTFUSION is again this kind of 3D mapping with depth cameras. And I can take two arbitrary frames from that video sequence from which I built my 3D map. I can take the frame on the left, I can take a point in that frame, I can project it into my KINECTFUSION model, and then I can reproject it into any other frame of that video sequence, because that works because, of course, the model itself was built from all these frames. Okay? And I can do this for any other sequence of points as well, and I can do this throughout the whole video sequence. Okay, so I can automatically generate arbitrary pairs of points for which I can say these points looked at the same point in my 3D environment, or these pixels. Okay, I can do the same thing for DYNAMICFUSION. Okay, just a model-based approach where I can take these points, track them through the sequence, and I can automatically generate training data that tells me which pairs of pixels look at the same point and which don't. Okay, and now what I can do is I can use this to train a neural network, and actually it doesn't really matter the details, it's the one on the right, but the idea is I'm going to train the network such that the input is a pair of images, and the loss function says whether those pairs of images, whether the center pixel looks at the same point or not. And I can again generate those examples from DYNAMICFUSION or KINECTFUSION. And then the goal for the network is to take this pair of images, feed it through a transformation, a sequence of function transformations, and in the end it should generate a feature descriptor for that pixel. Okay, which is kind of an arbitrary dimensional space that you might specify, 3 dimensions, 10 dimensions or more. And again, what the network should train is, or it should learn to say if 2 pixels look at the same point, their descriptors, their features should be very similar, and if they look at different points, then their features should actually be dissimilar. And that's the only supervision we give to the network. And Tanner actually explored that. He connected a big data set of himself. He took, I think, like 60 video sequences of him, and what you'll see here is just a subset. And what you see in each of them is kind of the color video, and then along next to it is kind of the DYNAMICFUSION model that we're building. And again, we can take this video sequence to generate many examples for a neural network that say same pixel versus not same pixel. And then the network learns a feature descriptor for these pixels. And what you see on this slide is what these feature descriptors then actually look like. So we color code these greenish, red, purple kind of colors. They indicate the descriptors of the pixels that the network learned. Okay, so we can take any of these video sequences and again generate those colored features, feature representations. And the nice thing is, what's really important here is that the coloring of Tanner is actually consistent across videos. even though we only gave supervision within videos. Okay? So the fact that the network learned a representation that is robust against very different lighting conditions and settings, we can now use this to transfer dynamic fusion models from one scene to the next. And I'll show you how this works. So imagine we have, here we build a dynamic fusion model of tenor, and now we have a different scene, different day, and we would like to match that model onto that next scene. Okay? So what we do is, we compute these learned descriptors, we compute them for the dynamic fusion model, and we can very efficiently compute the descriptors for the image of tenor that you see here. And now we can do a matching procedure that uses the similarity between these descriptors in order to say which model point should belong to which point in the right sequence. Okay? So here's now one example for how this then works. And this is on test data, so this is different scenes that the network had not seen before. But let's assume here's a sequence where we're building the dynamic fusion model. And now we take another scene, and we can just take the model from the left and snap it into the right scene and track it through. Okay? And again, this is a capability that dynamic fusion never had. But it was able to generate the training data such that the neural network can help us solve that problem. Okay? We can do the same thing with KINECTFUSION, where we have a 3D scene, okay, and we give again these correspondences. We train the network to learn features for this. And here's an example on, it's called the MSR7 scenes dataset, which is by the computer vision community. This is one of the standard test datasets, where the idea is you have a 3D map of a scene, and it's colored. Here you don't see the color in this one, but I'm going to give you a single camera image, and the system should generate the 6D pose of the camera, like the XYZ and the 3D rotation from that single image. Okay? And you'll see here how that then works, and here we show how we do this using, again, let me see. For some reason. Once more. Huh. Can't. Oh wait. Was there something? Oh, there we go. So what you see is on the lower right, you see the camera view that is presented to the system, and then we use learned features in order to match it into the scene, and you can see then the hypothesis of where the system thinks the camera view was. And that self-trained system is state-of-the-art performance on that data set. At least as of last time I checked. You never know these days, of course, with archive. Okay? But again, this is a very tricky scene to match, actually, because it has, with these steps, it has all these similarities, but the system was able to learn features that are very robust with respect to that. Okay? So this is just one example of how we can use kind of deep learning techniques in order to, and leverage model-based techniques in order to build systems that have capabilities that we just didn't have beforehand. Okay? So now I want to go...
1, 2, 1, 2.
3. So now I want to give you one example where I go also a little bit more into detail on some recent work that we've done on learning to predict kind of rigid object motion, and there's a lot of work going on in that scene, and I just want to give you kind of this example because it kind of illustrates how I think we can, rather than just using model-based techniques to train deep networks, how we can incorporate model-based ideas into deep networks themselves so that we get kind of to really tight integration of these different approaches. Okay, so this is work done by my student Arun, and the goal is, let's say, again, we have a depth camera observing a scene, let's say a robot manipulator or some objects being pushed around, and we would like to be able to learn from sequences of raw data. We want to learn to predict what's going to happen in the scene. What is the next frame going to look like? Okay? And ultimately, we would actually like to learn these predictive models then in order to control things in the scene. For example, we want to learn to use them to control a robot manipulator. I'm going to show you some examples for how we can actually do this. Okay? But again, the main notion is we want to do this from the raw training data with minimal supervision. Yeah? And again, there's a lot of interesting work going on, especially in the machine learning community as well in that domain. So ultimately, if you want to have a robot that can reason about these scenes in a way similar to what we humans do, of course, what the robot needs to learn about is that there are different objects in the scene, that objects have masses, that they have certain surface friction and all of this. So ultimately, I guess we would like to get there, but as you see, we're clearly not there yet. Okay, so the standard, let's say, deep learning approach to this problem would be the following. I have a depth image, so in this case, let's say we want to learn a predictive model for a BAXTER robot manipulator. Okay, so the input to the system is a depth image at time t, xt, and the input is also a control that we're sending to the joints of the robot, to the motors. And now we have some deep network, again, details are not important here, that is trained to tell me for every pixel in the scene how it's moving from one time step to the next. Okay, so it's a 3D motion for every single pixel. Now we can use such a flow then, if we add that flow to our current image, then we get a prediction for what the image would look like, the depth image, at the next time point. I hope that makes sense, right? So again, the network just tells us for every pixel, how are you moving? If we apply that motion to the current image, we get the next image. Now, if we want to train a network to do that, then the nice thing is we can just take the next image in the sequence to give us the loss function to tell us how wrong the network's estimate was. And then we can, just as I described early on, we can propagate that loss backwards through the networks in order to train the parameters of our network. Okay, so this is again just this backpropagation of the loss through the networks in order to update the weights. So we generate many sequences of images at time t along with control, then an image of time t plus 1, and then we're training the network to generate us these pixel-wise flows. Okay, here's an example now how this then works. And this is trained, you'll see the results are not very good yet. It's trained on not a lot of data, let's say. But what you see on the left is first a current input depth image. Okay. In this case, we want to train a model that tells us how objects move when they're being poked by this stick, which is controlled by a robot. Okay. So in order to highlight also kind of the deficiencies of these models, I'll do a multi-step prediction, which means the input is again the current depth image, and then we're going to give it a sequence of controls, and the network has to generate a sequence of future images based on these controls and the input image. So what you'll see is, again, the input depth image, the color is just for you so that you can see better what's going on. Then the future observation, which is what will actually happen in the future. And then on the right, you see the prediction generated by the flow network. So you can see that the network kind of learned roughly what's going on. It learned to kind of say what are the parts of the scene that typically move. But you can also see that somehow it's not very pretty, right? And the annoying part is that we know, for example, that these objects are rigid, and the network, by making pixel-wise independent predictions, is just going to generate objects that become fuzzier and fuzzier the more you predict them into the future. Okay, so based on that, we decided that we want to incorporate some information or some knowledge we have into that deep network in order to make it a bit more robust. So the idea is that, of course, in many scenes, what we have is, let's assume we have rigid objects. And we do know that rigid objects move according to a 3D translation and a 3-dimensional rotation. Okay, option 1 time step just moves, translates, and rotates, both 3D, and we can represent that transformation by a so-called SE3, which is just a parameterized way of modeling these transformations. And what we would like to do is incorporate that kind of knowledge about rigid objects and SE3 transformations into the network. Just very briefly again on these SE3 transformations, because you'll see some more of these frames. So on the left you see, for example, a BAXTER robot, and then the poses of the different parts of the robot, of the arm, they are represented by these so-called SE3 representations. And again, each of them is just a 3-dimensional rotation and a 3-dimensional translation. So these are kind of local coordinate frames that translate and rotate. You have on the right, you have an image of a cube, for example, that can also be represented as this kind of SE3 pose. Now, if we apply control to that, we get a change in these poses. Yeah? And the nice thing is that actually the motion of these objects we can also represent as SE3s. Yeah? So it's just now, instead of object position and orientation, the SE3 represents object translation and rotation from one time step to the next. And there's a very simple parametric way of updating those SE3s then. Okay? So this is kind of the knowledge that we would like to incorporate into our network. How we do this is, here's again, we take our flow network, and I already apologize, it might get a bit tricky, the slide's getting fuller, but we'll see how we get there. But again, this is our flow network, and what we do is the following. We add to this network another layer that says it's not only generating pixel-wise XYZ motion, but the network should actually segment the scene into different parts, which you see through this MT, which is what we call a mask layer. So the different colors here indicate, let's say in this case, the different parts of the robot that are moving. So each segment should represent a rigid object. And then in addition, for each segment, we predict the SE3 motion of that segment based on the control. Okay? So these SE3 motions, the network at this point doesn't know anything about what an SE3 motion is. It's just generating 6D parameters that are then interpreted by the next layer as if they were SE3 motions. Okay? And when we train that network, we still train it on the output, just on the pixel-wise loss function. Okay? So again, we do not tell the network anything about objects and masks. We just impose that on the structure of the network. Okay, and now we can train that network rather than the flow network. It's the same training. We don't give it any more supervisory data. And now you'll see the same multi-step prediction where the SE3 network is the second one from the right. Okay, and I'll show you sequence. And you'll see it's not perfect, but it's way better than the flow network. You can see that suddenly these objects behave more or less like rigid objects, which is the way we would want them to behave. Okay? So what the network learned is to segment out these objects, and it also learned the parameters of the SE3 transforms that describe well how they move. Okay? Oh, and by the way, they are cheap. So you know when you do Google search, it often gives you shopping advice or something like that. So I recently did a Google search for SE3 nets, and you can see you can buy them at Walmart for $21.96. Okay, and you can see they can do all these different things here. This is a real crop, so I didn't make this up here. But now the next step, what we would like to do with these networks is actually use them for control. Okay, where the idea is, and this is work again by Arun and also Franzi Meyer, who's a postdoc in the group. She's been working with him on this, where the idea is we would like to use these networks that not only predict how things evolve over time, but actually to control a robot manipulator. So the idea here is as follows. Let's assume this is a depth image, again, the current position of the BAXTER robot, and the coloring is the depth, so it has nothing to do with masks. And we would like the robot to achieve the position that you see on the right. Okay? So this is kind of like visual servoing, but now applied to the manipulator itself, where again, all we give the system is an image of the target, and how we can use this now for control is the following. We just hallucinate a zero control. We predict through our SE3 network the point cloud at the next time step, okay, which will, because it's a zero motion, will be most likely very similar to the input point cloud. Now, we can actually compute the delta between the predicted point cloud and the target point cloud, and we can propagate that delta backwards through our network, just like we do in training, but in this case, we keep the weights fixed. So what we're doing here is we're computing the gradient of our error function with respect to the controls. Okay, which people who do visual servoing know that's exactly what you often do in Jacobian control in these different setups. Okay, and now we can apply that control to the system. The one piece that's really ugly here is that in order to do this, we need for the loss function between the prediction and the target, for every pixel we need to know the data association between them. Okay, so we need to know that pixel should move over there in order to achieve the target point, and only then can we propagate that back. So that brought us to a next generation of these SE3 nets, which we call SE3 post nets, and I'm not going to go into the details here, but this was the SE3 net, and this is yet another complication in here, but these are what we call, again, SE3 post nets, where the idea is we force the network to not only generate object parts and masks, but for each object, the network should also generate for us an SE3 pose, a 6-dimensional pose for where the system thinks this object is. Okay, and this pose is trained to be consistent with the motion that the network also predicts. Rather than going into the details here, I'll just give you kind of the highlights of what this is really about. So again, we generate masks, so we segment the scene, and for each segment, the system also needs to generate a 6D pose for each object in that scene. Then these pose estimates need to be consistent over time with the motion that we're generating. The key trick is that we're not giving any more supervision to the network. We're only adding additional constraints into the structure of the network. And now we can do control in the pose space without us having to give any explicit data association. So how this works is as follows. So let's assume we have our current image, we have the target image. We can use this network now through this pose mask to give us target poses for the different parts in the scene. Yeah, so each of those is just a 6D pose. We apply the same network to our current image. That gives us also 6D poses for our current image. Okay, so again, rather than giving us these transformations for pixels, it's giving us transformations for parts in the scene. And then we can do the same forward control with the error computation, and we can do the same back propagation to give us the control. But the key difference here is that this error that we're using works without any manual supervision because the delta is now computed in this pose space. Okay, let me just show you a video for how this works. Okay, so in the lower part, what you see is the target. Okay, this is the pose we would like the BAXTER to achieve, where you see on the left, of course, the color, and then the depth image. The depth image is what we really use. So what the system does with this depth image, it generates, first of all, 6D poses for different parts in that image, which are the parts of the robot, and it generates a segmentation, which you can see on the right side, indicated through these colors. So you can see that the network learned to segment the arm into different parts. We can now also take the current image, which is given on the top row, do the same thing where for the current image we compute these poses given in these solid lines, and now we can use the delta between these poses in order to generate controls. So you can see this here now. Again, we're not giving any supervision to the network on kind of data association or so. The network really learned internally to mask the scene and to generate consistent estimates. Here's another example. So you can see how these poses, the pose space, is kind of fused to match it against the target poses, right? And then in the end, actually, you can see that they match very well. Okay? And all of this is done in this embedded learned space, so it's not done in any pixel space anymore. So this works actually at 30 frames a second because we can compute all of these things very efficiently. One final example, and then I'm done. Okay, so this is kind of visual surveying, but the network learned to detect different parts in the scene. So from a high-level perspective, what I'm excited about here in this context is really that the network learned, just by giving it pixel-wise motion estimates, it learned something about objects, right? So if you look at these masks, it learned something about different parts of the scene, and it learned a consistent pose space, which means it learned to detect those things in the scene as well. Okay, so now I want to briefly discuss and then wrap up. So in general, models and deep learning, so on the one hand side, as I said initially also, these model-based approaches have the advantage they are highly accurate. They have very broad applicability because they just model the physics of the scene, but they often only work in a local basin of attraction. Okay? On the other hand, deep learning it can give us, if it's trained well, give us systems with much larger basins of attraction. For example, it can be used to initialize model-based approaches, but the key disadvantage of those approaches is that they often only work in the trained regime. Okay. The main difference between robotics and what we often see in computer vision is that we're not dealing with independent images, but we're dealing with sequences of images that a system observes in the world, or sequences of controls, and we can leverage that in order to train deep networks, even using local optimization-based techniques. Okay, and I think ultimately, really what this is about that, you can use deep learning and incorporate model-based approaches, like what I showed you, seamlessly into the network structure itself. Again, because it's not about there's deep learning and here are the models. Deep learning is just a sequence of functions that we apply to our data and that we learn through backpropagation. And inside these functions, we can easily incorporate model-based approaches. It's just another function. All we need is kind of the derivative of these functions, and then we can train them seamlessly in the same framework without having to distinguish even between models and the deep learning parts themselves. Okay. There are, of course, many open questions. So again, with these SE3 nets, we showed that we can bootstrap systems that can start learning about objects and their motion, but ultimately we want to have much more higher level understanding of a scene than that, and the question is how far can we go with these techniques? It's not clear to me yet how far we can really get. Also, how can we learn reusable components? For example, if a system learns about motion of objects, it should be able to apply that in very different scenes as well. And so it's not going to be one monolithic big deep network that does it all for us, but there should be some components that individually learn useful things that can be reused in the future. Of course, all this model-based kind of deep learning that I discussed here also can be used in deep reinforcement learning, and there's going to be, of course, a lot of interesting work how you can really do this, and also how do we get uncertainty estimates. One final, of course, thanks to all the great students that I worked with in the lab, also postdocs and other collaborators, and various funding sources. And Wolfram already mentioned that. One quick note is that I'm gonna, starting next Monday, take a partial leave from University of Washington. I'm gonna put a robotics research lab for NVIDIA next to the university, where we're gonna hopefully do some cool research. So if you're interested, feel free to get in touch. And later, after the questions, I can show. I showed this at RSS. There's a cool video here that I'm going to show you, but I want to do that after the questions, and so that other people can go to the break if they don't care. Thank you very much.